I'm Pedro Chu. I'm located here in Southern California. I'm a lead application engineer, and today the topic will be on meshing when a good mesh is not good enough. Okay, and I'll show you how you can use Mark to achieve better results with automatic remeshing. So here's the today's agenda. I'll be talking about adaptive remeshing. I'll be talking about when should we use adaptive remeshing, the two different types of remeshing implemented in Mark. We'll see some application examples. We'll see how this adaptive remeshing has been implemented in Mark. I'll show you Mark model where adaptive remeshing is done, and then we'll come back for a summary. Okay, so as engineers, we all have heard the term garbage in, garbage out. And in analysis, nothing is more true than that. We need to have the right material models to be used. We need to specify loads and boundary conditions correctly. And also, we need to have a mesh that is, let me just turn my arrow on. So we need to have a mesh that is has a good quality, so that, that the results will be reliable. We need to have this mesh refined in the areas that we are concerned about stress gradients, okay? And we can make it coarse in regions that are not of much concern. So for example, if you take this model here in this animation, initially the mesh is just, I don't think you can ask for a better mesh than that. But because of the load being applied, because of how you want the material to flow, and it has to conform through this the die in here, okay? If you don't do anything with the analysis will stop right here, because eventually the elements get so badly distorted that the solver just cannot continue. So you need something. You need to do something with your mesh so that the analysis can continue. And this something is a tool that we call remeshing. So remeshing is any change that is made to the original mesh during the analysis. You can do these changes in the mesh manually, or it can be automatically done. And if you're going to have capability like that, you have to have control of when you want the remeshing to take place. So when do you use adaptive remeshing? Okay, whenever you have a high stress and strain gradient, whenever you have element distorting extremely. So if we look at this example here, initially the mesh was very good quality, but you can see that as it deforms, the original mesh cannot be used to represent a configuration like this. This example is a very simple example. You can start with just a cube with a box, and as you deform it, you can also see that the original mesh will not be enough to simulate this type of deformation, and therefore you need some sort of a remeshing technique to modify the mesh and to let the analysis continue. And more recently, we have been developing a lot of features to be able to simulate fracture mechanics and crack propagation. So you can see in this example, you have a rigid contact body fixed at the bottom, another rigid contact body torsioning this contact body, and you can see that how the crack is propagating here. If you don't have adaptive remeshing, basically the best you can do would be to simulate a crack propagating along existing mesh. So you have to know how the crack would propagate. With global adaptive remeshing, that allows you to simulate any sort of crack propagation in your model. So MARC has two types of adaptive remeshing. We have a local adaptive remeshing, and we have a global adaptive remeshing. And in the next few slides, we'll be talking in a little bit more details on the difference between these two adaptive remeshing in MARC. So local adaptive remeshing. Local adaptive remeshing works on a set of elements. So you can have an original element like this, you can have several elements, and when certain conditions are met, what the solver will do is will take the element and just subdivide the element like this. Okay. You can define several levels of refinement in MARC. So level 1 allows the element to be subdivided only once. Level 2 allows the element that were subdivided first to be subdivided again. Level 3, you can also resubdivide again the element here. And every time an element is subdivided, what MARC will do is will write the constraint equations between the newly created node with existing nodes. So for example, if you have a situation like this, and then you specify, let's say, penetration is as one of the criteria for remeshing. So whenever you see the solver detects penetration, what it will do is that it will take this element, subdivide it like this, get rid of penetration, write the constraint equation, and then continue the analysis. So this is a local adaptive remeshing. Global adaptive remeshing on its hand works with a contact body. So in MARC, what you do is if you have a piston rod like this, for example, you could define this entire mesh as a contact body, and then when the remeshing criteria is met, what MARC will do is will take this contact body, create a new mesh, and then continue the analysis. So my presentation today will be focused on global adaptive remeshing. Okay, so all I'll be talking about today will be on global adaptive remeshing. So when you are working with a global adaptive remeshing, you need to specify criteria when you want the adaptive remeshing to take place. Okay, and there are several criteria available in MARC. You can specify the frequency that you want the adaptive remeshing to take place. Okay, so I want the remeshing to take place every 5 increments, for example. Or you can specify stress and strain criteria. So whenever the stresses and strains change a certain amount from one increment to the next increment, it will automatically create a new mesh. You can define element distortion as a criteria as well. Contact penetration. You can also define a local refinement. So instead of just going and define, let's say I want a new mesh to be created, and this new mesh will have a certain element edge length, you can actually go and specify this area I want to have a finer mesh, a different area I want to have a coarser mesh. And these remeshing criteria can be used for both 2D type of analysis, 2D type of elements, and 3D analysis and 3D elements. So when you in Mantec, when you go to define a remeshing criteria, these would be the methods available to you. So here you're talking about for 2D type of analysis, axisymmetric, plane stress, plane strain. Here you're talking about shell elements, and here you're talking about solid elements. Okay, so industry application, as you can see, in almost every industry where you see extreme deformation, where you see that the original mesh cannot be used anymore, you can use adaptive remeshing. So from aerospace to biomedical, electronics, oil and gas, automotive, consumer electronic products, and so on. So here we're seeing a I want to show a few application examples. So this is a packer that is used in the oil industry. And typically these components will be operating in under the surface, several hundred meters or even thousands of meters beneath the surface. And the function of these packers is to avoid or to stop gases and fluids, okay, from reaching the surface, because a lot of times these gases could be toxic gases, okay, and you don't want it to reach the surface where the operators are. So you have a tremendous pressure being applied in here, and you can see that the packer initially has a very just simple geometry, okay, and upon application of this pressure, you want to make sure that no gas or no fluid will escape this containment here. Okay, so you can see that this geometry here requires a new mesh. The original mesh cannot be used in this case. Another example in here would be a cutting operation. Okay, so as you can see, the cutter cutting through the workpiece, and then in the end, even you can simulate the chip separating from the workpiece. So in this case, I'll be using a user subroutine to simulate this chipping falling off. Okay, and again, in this case, this example, I'm showing the temperature, so this would be a coupled thermostructural analysis where you have the cutter cutting through the workpiece. You have friction between the cutter and the workpiece. Friction generates thermal gradient, okay, and then you can simulate, you can predict what is the temperature and the deformed shape as well in this process. Another application example is for crack propagation. So you can see for a 2D type of analysis, you can see how crack is propagating. You can see for 2D type of elements, shell elements, where the crack starts in here, and actually the crack will reach bifurcation, okay, and then Mark is able to allow the crack to bifurcate. And also for 3D type of analysis, where you have an initial crack in here, and for the 3D type of analysis, solid elements, you can also see remeshing and then the crack propagating through this block. So what are the adaptive remeshing steps in Mark? Basically, you start the model just as in any usual Mark analysis. You create a mesh, you define your materials properties, you apply load boundary conditions, you have all your contact definition just as usual, just as any Mark analysis. And here you come and you define remeshing criteria, and you just need to make sure that in your load case you select whatever remeshing criteria that you want to use in the analysis. So the remeshing implementation in Mark, what Mark will do internally is that the remeshing criteria will be checked at the end of every increment. Okay. If the remeshing criteria is met, Mark starts the remeshing procedure. It creates a new mesh based on the deformed shape. Okay. It will do a data mapping. So all the stresses and strains from the current mesh is transferred to the new mesh. Boundaries, loads and boundary conditions are also mapped to the new mesh, and then the analysis just continues. So this is just internally what Mark will be doing. So I want to do a quick demonstration, show you a model of rubber seal that is subjected to pressure loading. So I have an O-ring, and I'm just modeling a section of this O-ring. I could just use a plane strain analysis for this example, but I wanted to show a real 3D model being analyzed here. So this picture here shows the different contact bodies used in the analysis. So I have one deformable contact body, which is the seal, and then I have these green contact bodies are the symmetry contact bodies. I have a fixed contact body here against which the seal is going to be compressed, and then I have this contact body here, which I call down. So I compress the seal, and then the pressure is applied. Please notice that because I don't know how the final shape of the seal is going to be, therefore I don't know which phases I should be applying the pressure. So what I do in this model is that I apply the pressure on a set of elements that I think will have pressure. And Mark has a feature that he tells that if you have a pressure being applied on an element face, if all the nodes on this face are in contact, it deactivates the pressure on this element face. Okay, so the moment that one of the nodes is not in contact anymore, then the pressure on this face is activated, and then the pressure is applied to this element. So this is a very powerful, very convenient tool for this type of analysis. Okay, so in this model, I will have a pressure loading, we'll have contact bodies, symmetry, we have adaptive remeshing, and also I have a local refinement. I don't want, or I don't need fine mesh everywhere in this seal. So what I can do is I can just define an area around this fillet and around this fillet, and I say that, okay, I want the mesh finer in these areas here. Okay, so this is going to be the final deformed shape, and you can see that initially when I compress the O-ring, it is going to be symmetric. Okay, and then when I start applying the pressure on this side here, you can see that I start exposing some of the elements that were fully in contact initially, and then as they become out of contact, then the pressure is being applied to them. And eventually, ultimately, what I want to determine here is that, you know, the pressure that I apply here, is it the seal still going to be sealing what it is supposed to seal? Okay, so let me go to Mentat. So this is my Mentat model. Okay, what you can see here is that here is the menu tree for Mentat. You can see the material model that I have defined. Okay, so it's just a Mooney with a constant C10, C01 defined. I have my contact bodies here. I have my deformable contact body. I have my fixed contact body. So it is velocity controlled with zero velocity. So this rigid contact body is just fixed in space. I have this down contact body, and it is a velocity controlled. And what I do is that I am applying a velocity of a 0.3 negative in the y direction. And then this table velocity controls the movement of this contact body. And this table velocity, what it is that from time, so I have basically two load cases here. The first load case, I'm compressing the O-ring, and the second load case, I'm applying the pressure. So load case 1 is from time 0 to 1. And so from time 0 to 1, the velocity is going to be minus 0.3. And from time 1 to time 2, when I'm applying the pressure, I maintain that the contact body fixed, and just the velocity is 0. Okay. And then I have my pressure, a boundary condition. I'm applying a pressure of 1200 psi. The table pressure is controlling the pressure application. And here is that feature that I talked about, load active in contact. By default, all the load, the pressure load is active whenever, regardless of the nodes are in contact or not. But if I deactivate that, what Mark will do is we'll check for all the nodes in the phase where the load pressure is being applied. If all nodes are in contact, then the pressure is deactivated. Okay, so I just want to show you this pressure table. So what it is from time 0 to 1, I have a pressure of 0, and then from time 1 to 2, I'm linearly ramping up the pressure. Okay. So I have my pressure application. So all the way up to this point, and I have my contact table as well. Okay, so my contact table, I just define friction, and I define that that my CO is in contact with all my rigid contact bodies. So all the way up to this point, this is just a regular mark analysis. So the adaptive remeshing that you do is you go to adaptive mesh adaptivity tab, and you go to new, and then here are the different remeshing methods that you can specify. So since I'm dealing with a 3D contact here, 3D type of element, I'm going to choose a pattern tetra for as my remeshing method. Okay, and in my remeshing method, you see the names adapt G2. Okay, and here would be the remeshing criteria that you can specify. I can go and say I want to be remeshed every certain number of increments. Okay, I can request immediate remeshing, and I'm going to just use this immediate remeshing in this case. You can go to advanced, and in advanced here you can choose. I want the remeshing to take place whenever my strain changes by this amount, or if I have penetration, or if I can use a volume ratio as well. So in this case, I'm just going to use a strain change and penetration. Okay. Here I can specify the element edge length for my model. So in this case, I'm going to use 0.08. And in advanced, I can have my local refinement. So I can go and specify a local refinement around here, this fillet, and around this fillet as well. Okay. So I'm going to specify the different boxes. So the first box, one here, and I can specify the levels I want. So I'm going to go with level 2, 2 levels, which means in this refinement box that I defining here, you can refine the element time size will be 0.08 divided by 2 divided by 2. Okay. So for corner 1, I'm going to specify this point. For corner 2, I specify this point. And then I can say that these boxes will be moving with my fixed contact body, which means it is not going to move. Okay. So what this allows you to do is that you can, if you have this contact body moving, you can actually define this refinement box to move with this contact body. And I'm going to do the same thing for box 2, refinement level 2, and then we're going to define it in this area here. So the first corner, I'm going to pick this point. Second corner, I'm going to pick this point here, and body fixed and body fixed as well. Okay. And lastly, all you need to define also need to define which contact body I want to use for this remeshing criteria. So I'm going to use a CO. Okay. So that's all I need to do for my remeshing criteria. And then I need to make sure that in my load cases, and I'm just going to show you, okay, down, that I have my loads selected. And then in the global remesh, I need to go and specify which adaptive remeshing criteria I want to use. Okay, so I already had adapted G1, and I'm just going to use adapted G1. Okay. Same thing for load case 2, pressure. Make sure that you specify which remeshing criteria you want to use in your analysis. And then you go to your job. Okay. Select the load cases that you want to run. Okay. And then you are just ready to go and run the analysis. Okay. So you run the analysis. I'm not going to run this analysis. It took about 11 minutes to run. Okay, and you can see exit number 3004, and you can just open the results. And so you can look at the um, your deformed shape. You can just step through it. And one thing you can see is that by defining the remeshing uh, refinement boxes, as expected, the mesh around this fillet and around this fillet here is much finer than elsewhere in the model. Okay, so these just allows me to control how I want the mesh density in my remeshed body. Okay, so I can look at the total equivalent strain, and you can just step through the different increments. So you can see that this is about increment time 1.08. So I already started the load case number 2, which is the pressure being applied. Okay, and I just wanted to show you um, how Mark is applying the pressure in here. Just make sure that I don't have pressure being applied on the top or pressure being applied on the side here. So I can go to style, vector, I can choose the external force, okay, and I can turn that on, okay. So if I put it on a side view, so I can see that these are the nodal forces being applied due to the pressure on this side here. If I go back to time 1, which is at the end of the compression stage, there is no pressure applied in here. The moment that I go to the next increment, okay, you see that now I'm ramping up the pressure application. Okay, so that's just to make sure that this is what the Mark is doing. And if I go to the contour plot, okay, I can go to the last increment, and then you can see the last increment. That's how the deformed shape looks like. Another thing that you can do in Mark, in the post-processing, is particle tracking, for example. In the beginning, the O-ring was just a circular shape, and sometimes you want to know, okay, what happens to the material? How is the material flowing as the O-ring seal is being compressed? So we can go to the sample points here, and then just turn the nodes on. And what I can do is, let's say that I want to see on this side here, how did this node get to this point here? So I can do a material particle tracking, and I'm going to specify this node here. I'm going to specify, I don't know, just arbitrarily pick a few nodes here and even a node in here, okay? And do a right mouse click to accept these 4 nodes, okay? Then I can go to track plotting. I'll say all points. This will take a few seconds because of the T16 file. The results file is about 400 megabytes. So Mark Mentat has to go through the entire T16 to gather all the information to be able to do this, to track this particle tracking. Okay. So right now it's going through, so it's done. And what I can do is I can just do tracks. Okay. Let me turn the node off so we can see better. Okay. So what you can see in here is that those nodes that I specified, okay, that's how initially they were here, and that's how they are moved. Here is when they were fully compressed, and then here is when you start applying the pressure. Okay, so if I go to the first increment, okay, you can see originally where the nodes were, okay, and then I can just go hit play, and then you can just see how it is deforming. Okay, and how the material is going. Okay, the material is here, and now the pressure being applied, it goes to its final location. Okay, so these are some of the things that we can do with adaptive remeshing. Let me go back and just do a summary. So hopefully I was able to show how easy it is to use adaptive remeshing in Mark. You can also see that by using adaptive remeshing, automatically the solver will improve the mesh quality on the go. So basically, in this case, no user intervention is needed. It gives you, adaptive remeshing gives you the ability to solve very, very hard simulation problems. Okay, so you can see that something like this would take several interventions from the user, several restarts probably, if you didn't have access to adaptive automatic adaptive remeshing. And hopefully this will give you improved productivity in your analysis. Okay, so that's all I had to show today. I think we have some time for Q&A. I put my email address in this slide. So if you have any questions, if you don't get a chance to ask today, please reach out to me. I will try to get back to you as soon as I can.